indeed see them. Yeah, I guess since it's 3 and the recording is in progress, I guess that's the sign that we can start. So it is my absolute pleasure to introduce Vicent Pérez Calabuig from the Universidad de Valencia, who will present to us about left nilpotent skew braces of class 2.
Okay, thank you very much, Arne. Well, first of all, of course, I'd like to thank the organizers, Ivan, Salvatore, Mikola, and Jobir, for inviting me to participate today in this European Non-Associative Algebra seminar. Well, as you can see, the main topic of this talk is on left nilpotent skew braces of class 2, and this is joint work with professors Adolfo Ballester Bolinches, Leonid Kurdachenko, and Han Yang-Baxter. I don't know if everyone here is familiar with the study of skew braces, so let me start with a quick overview on the origins of skew braces and its relations with the study of solutions of the Yang-Baxter equation. Well, probably the starting point is the well-known publication of Drinfeld in 1992, where he established a list of some unsolved open problems in quantum group theory arising from the study of solutions of the Yang-Baxter equation. So here pose the attention into the so-called set theoretical solutions of the Yang-Baxter equation. Then the basis for the algebraic study of these solutions was given in the seminal papers of Gateva Ivanova, Vandenberg, and in Etinhoff, Schiller, and Soloviev. In these works, we find that non-degenerate and involutive properties of set theoretical solutions have a very good algebraic behavior because they can be characterized in terms of algebraic structures. In particular, the development among them, we have the development of the theory of skew braces, because every skew brace provides a non-degenerate solution, and vice versa. Every non-degenerate solution has an associated skew brace controlling it. And therefore, the main philosophy here is very clear. The more we know about the structure of skew braces, the more we progress into the classification problem of non-degenerate solutions of the Yang-Baxter equation. In particular, one of the most studied classes of non-degenerate solutions are the so-called class of multi-permutation solutions. Their importance lies on the fact that computer experiments are showing more and more that almost every finite non-degenerate involutive solution is multi-permutation. And in addition, the study of multi-permutation solutions can be addressed in terms of an algebraic property of skew braces. Namely, nilpotency notions of skew braces provide a very good framework to analyze this class of solutions. So my aim here is to present you our structural study of left nilpotent skew braces, class 2, and the applications to the classification of multi-permutation solutions. Okay, so let me start with the definition of skew brace and some notation. So we know that the skew brace is a set with two group structures, an additive group and a multiplicative group, not necessarily. We have the following kind of distributivity property. A times B plus C is equal to A times B minus A plus A times C. We will see later more intuitive explanation of this disturbing minus A element. Okay, so we have two groups, so we have two identity elements, one for the multiplicative group and 0 for the additive group, but it turns out that applying this distributivity property, both identity elements coincide. And we are going to denote it by 0, because somehow we have that the additive group plays a dominant role in the study of skew braces. Indeed, if X is a class of groups, then a skew brace is said to be of X type if the additive group belongs to X. Well, skew braces were first introduced by Room in 2007. Indeed, Rom called them braces. And braces were introduced with the additive group abelian because Rom realized that the abelian character of the additive group of a brace characterizes the involutive character of the non-degenerate solution associated. So later on, Warnier and Benjamin give the general solution, the general definition where both groups are not necessarily abelian. So we can see Rom's braces as skew braces of abelian type. Okay, so let's see a couple of examples. The first example shows that the class of groups can be seen as a particular class of skew braces where both group operations coincide. This is what we call the class of trivial skew braces. Another example consists on considering the multiplicative operation as the opposite of the additive operation. And in this case, we also obtain a skew brace structure that we call almost trivial skew braces. Okay, so now look at this term appearing in the previous distributivity property. If we look at this term, we can set for every pair of elements A of B, lambda A of B equal to minus A plus A times B. So with this setting, we can see that every lambda A is an automorphism of the additive group for every element A in B. And even more, the map sending each element to its corresponding lambda is a homomorphism. And this makes the multiplicative group acting on the additive group by means of this lambda map. This is what we call the lambda action and plays a key role in the inner structure of skew braces. Indeed, it allows to write products in terms of sums. And therefore, the previous distributivity property has a more intuitive way in terms of the distribution of the lambda action. Okay. And also, for instance, the reason for calling trivial skew braces those braces is because in this case, we can see that in this case, the lambda map or the lambda action is trivial. Okay, so now, if we want to define nilpotency notions in skew braces, we need what we call a star operation in skew braces. But first, let me give you the following remark. If R plus star is a ring, which means that R plus is an abelian group and R star is a semigroup, we have that a ring is a Jacobson radical ring, which that is that the Jacobson radical coincides with the whole ring, if and only if the ring with this operation becomes a group. This operation is a dot operation given by R dot S equal to R plus R star S plus S. So in a similar way, we can think in the other way around. If we have B plus dot skew brace, which means that B plus and B dot are groups, we can define the so-called star operation of B as A star B equal to minus A plus A times B minus B, which can be written in terms of lambda in this way. Okay, so here this is the key fact. This star operation is in general non-associative, but if the skew brace is of abelian type, which means that the additive group is abelian, then we have that this star operation is associative if and only if B plus the star is a Jacobson radical ring. And this is the reason why Rom's braces were considered as a generalization of Jacobson radical rings. And for instance, we can apply ring theoretical methods to study the structure of skew braces. Indeed, we can also apply group theoretical methods because we can also consider the following construction. Given a skew brace B, since the multiplicative group acts on the additive group, we can create the semi-direct product of the additive group times the multiplicative group by means of the action lambda. I don't know if you are familiar with this notation, but this means that this is the normal subgroup and this is the subgroup acting on the normal subgroup with the action lambda. Okay, so this is a semi-direct product, and if we look at this commutator in this semi-direct product, we have that for every A and B elements of B, the commutator 0A and B0 becomes the star product of A and B using the lambda action I said before. So we can see that the star products can be seen as commutators in the semi-direct product associated to skew. Okay, so let's see how this star product looks like in our previous examples. In trivial skew braces, we have that both group operations coincide, and therefore we can see easily that the star product is a null operation. And what about almost trivial skew braces? Well, in almost trivial skew braces, the product is the opposite of the sum, and therefore the star product uh, becomes an additive commutator. So these observations are very inspiring. Indeed, one can think about iterating star products until getting a null operation, and therefore nilpotency notions naturally arise. Okay, so before, we need the following definition. A subset X of a skew brace B is called a subbrace if X with the restriction of the operations becomes a skew brace. And then we have that the star product of subsets X and Y is defined as the additively generated subgroup of all possible star products of an element of X and an element of Y. Okay, so we have all the ingredients. Now we can introduce a iterated series of star products by goal. Remind that we have seen that the star product is in general non-associative. Therefore, if we want to iterate star products, we have to distinguish sides of operation. On one hand, we have that if we iterate the star product of B on the left, then we get a descending series of subbraces, which is called the left series of B. And what about if we iterate the star product of B on the right? So similarly, we obtain also a descending series of subbraces, which is called the right series of B. And therefore, a skew brace is said to be left, respectively, right nilpotent of class M if M is the latest term of the latest non-zero term of the left, respectively, right series of B. Okay, so let's see a couple of examples. If we continue with our previous examples, we have that trivial skew braces are left and right nilpotent of class 1 because B star B is equal to 0. And what about almost trivial skew braces? Well, we have seen that the star product in almost trivial skew braces can be seen as an additive commutator. Therefore, it is easy to see that in almost trivial skew braces, both left and right series are the lowest central series of the additive group. And therefore, B is left and right nilpotent of class M if and only if the additive group of B is nilpotent of class M. Sorry. But okay, if we look at these examples, does it mean that left and right nilpotency are equivalent notions? Of course not. We have also an example of a skew brace of order 6, whose additive group is isomorphic to a cyclic group of order 6. The multiplicative group is a symmetric group, and it is right nilpotent, but it is not left nilpotent. And on the other hand, we have also an example of a skew brace whose of order 8, whose additive group is a two-elementary abelian group, and the multiplicative group is a dihedral group, and it is left nilpotent, but it is not right nilpotent. Okay, so in view of these examples, the following question naturally arises. What is the role of left and right nilpotency in the study of the structure of skew brace? Well, so this question can be answered in these results. The first result is a result of Sedot, Smoktunovich, and Benjamin, and it says that if B is a finite skew brace nilpotent type, then B is left nilpotent if and only if the multiplicative group is. The result was also proved by Esther Bolinches and Esteban Romero using group theoretical methods applied to the previous semi-direct product associated to a skew race. And this shows that left nilpotency has a very good behavior in terms potency and in potency associated to the semi-direct product associated to B. Okay, so and what about right nilpotency? Do we have a similar result for right nilpotency? Well, unfortunately, no. But the good thing is that, sorry, the right nilpotency characterizes the multi-permutation character of solutions. Right? Sorry. So we have the following result of Thedo, Jespers, Kubat, Van Antwerpen, and Perwin, showing that a solution of the Yang-Baxter equation is multi-permutation if and only if the associated structure of the associated structure skew brace is right nilpotent of nilpotent type. Okay, so I would like to remark the nilpotent type hypothesis in both results. And this is because out of the nilpotent type universe, life is very wide. Indeed, one can construct easily counterexamples of these results in the non-nilpotent type case. For instance, for the first result, we take a finite trivial skew brace isomorphic to a simple group. Then, of course, it's left nilpotent because B star is equal to 0. But the multiplicative group is far away, is simple, and therefore it's far away to be nilpotent. And the same holds in the case of the second result. If we take a solution whose structure skew brace is a trivial skew brace isomorphic to a simple group, then it is right nilpotent because again B star B is equal to 0, but the solution is also far to be multi-permutation because we cannot consider quotients as we are working with a simple group. So in the sequel, we are going to pay a special attention to the nilpotent type case, which means that the additive group is nilpotent. Okay, so the next natural thing is to define skew braces which are both left and right nilpotent. And this was done firstly by Smoktunovic by fusing both left and right series of iterated star products. Indeed, we can say that a skew brace is strongly nilpotent if and only if it is left and right nilpotent. And if we focus on the nilpotent case, we have that strong nilpotency coincides with the central nilpotency introduced by Bonato and Jedlicka in terms of the center of a skew brace. Okay, so we have that in this case that skew braces are both left and right nilpotent. We have both the two good characteristics. We have a good algebraic behavior, and we have also a way to characterize multi-permutation solutions. So here the aims are very clear. The main aim is very clear. The aim is try to give easily to check sufficient conditions to ensure either left or right nilpotency. So the first approach consists on considering angle type elements for the star product. So observe that if B is left nilpotent of class M, then for every element B in B, we have that the star product of B by itself, iterated on the left, is 0 after M times. And the same holds in the case of right nilpotent skew braces. So we can think about the following definition. A skew brace is said to be left nil of class M if M is the smallest natural such that for every element B skew brace, B is M left nil in the sense of the previous equation L. And similarly, we can also define right nil for right nil on the right. And even more, we can say that a skew brace is strongly nil of class M if M is the smallest natural such that for every element B, any star product of M copies is equal to 0. Okay, so we have the following general situation. We have seen an example of a left nilpotent skew race which is not right nilpotent, and we have seen an example of a right nilpotent skew race which is not left nilpotent. Now we have introduced weaker nilpotency notions, left nil, strongly nil, and right nil. So the natural question is, do these conditions imply left, strong, and right nilpotency respectively? Well, the previous result of Sedos, Muktanovich, and Vendramin showed that these two nilpotency notions are equivalent in the abelian type case. And it remained open, as an open question, what about the other two implications? But then, in a recent joint work with Ballester Bolinches, Ferrara, and Trombetti, we showed that these two implications are in general false. And even more, we prove our main result gives, nevertheless, a sufficient condition for ensuring the strong nilpotency in terms of strong linear. We prove that if B is a finite skew brace of nilpotent type, then if B is too strongly nil, which means that B star B is equal to 0 for every element, then B is both left and right nilpotent. And if we look to the example showing that these two implications are not true, these examples show that the result is the best we can get in this sense, because here we found a skew brace of order 32, which is isomorphic to a two-elementary abelian group, so it's of abelian type, and it is 3 strongly nil, and in particular 3 right nil, but it is not right nilpotent, and of course exactly not strongly nilpotent. And we have also another example showing that the nilpotent type hypothesis is necessary, because we have an example of, if we take as an example an almost trivial skew brace isomorphic to a symmetric group of degree 3, then easily this skew brace is too strongly nil, but this skew brace is neither right nilpotent nor left nilpotent. For the second approach, let's look again to our previous example showing that both left and right nilpotencies are not equal. So if we look at these examples, we can see that in this example shows that 2 is the smallest right nilpotency class that does not ensure left nilpotency, because trivial skew braces are left and right nilpotent of class 1. So here we have that 2 is the smallest right nilpotency class. And if we look at the other example, we have that this example is left nilpotent of class 3, but it is not right nilpotent. So here the natural question is, what about for left nilpotent class 2? Does it imply that the skew brace is right nilpotent? So this is the starting point of a joint work with Ballester Bolinches and Kurlacek. Our first answer to this question, of course, is not. In general, we can find easily an example of a skew brace of order 6, which is isomorphic to a symmetric group, whose additive group is isomorphic to a symmetric group of degree 3. And such that it is left nilpotent of class 2, but it is not right nilpotent. But if we look at this example, we see that this example is the additive group is non-nilpotent. So it remained open the case of nilpotent type. And in this case, we get a positive answer. Our main result shows that if B is a skew brace of nilpotent type, and it is left nilpotent of class at most 2, then B is right nilpotent. And even more, we got an upper bound for the nilpotency class of B. Indeed, if M is the nilpotent class of the additive group of B, and R is the nilpotent class of the additive group of B squared, then we get this upper bound equal to 2 plus M times R plus 1. Okay, so the first application of this first main result is applies to the classification of multi-permutation solutions. We have that every non-degenerate solution of the Yang-Baxter equation, whose structural skew brace is of nilpotent type and left nilpotent of class 2, is a multi-permutation solution. And the second corollary from the result is the case of abelian type, because in this case we have a particular right nilpotency class, because M is equal to 1, R is equal also to 1, and therefore if B is left nilpotent class 2 of abelian type, then B is right nilpotent of class at most 3. And in this case, this upper bound for the right nilpotency class is effective because we can also construct a brace of order 8, whose additive group is abelian, of course, and it is left nilpotent of class 2 and right nilpotent of class 3. And this result opens the door to solve probably one of the most difficult problems in the study of the structure of a skew brace, which is the problem of determining the structure of a finally generated skew brace. So let me give you the following definitions. If we have B as if B is a skew brace and X is a subset of B, we define the subbrace generated by X as the intersection of all possible subbraces containing X. And then we can say that B is finally generated if we can find a finite set such that the generated subbrace by X coincides with the whole B. In this case, if X has R elements, we can say that B is R generated. Okay, so here we have the following open problem. If we have a finally generated skew brace, what is the structure of this finally generated, this brace? Well, this is, as I said, one of the most difficult problems, and just to figure out the difficulty of this problem, think about the case of groups. We know that one-generated groups, which are cyclic groups, have a very well-known structure. Nevertheless, to define or to characterize the structure of one-generated skew braces is a problem of extremely difficult. Indeed, we only have some partial results in the case of one-generated braces. So if B is a one-generated brace, which means that the additive group is abelian, we have some partial results in the case of B being left nilpotent of class 2. This was given by Kurdachenko-Subotin, and also we have a characterization of the structure of one-generated brace if B is right nilpotent of class 2. This also was given in a joint work with Ballester, Bolinces, Esteban Romero, and Kurdachenko. So from now on, we are going to focus on the general case. So we are going to focus in the case that B is a finally generated left nilpotent brace of class at most 2. So we are considering braces with the additive group abelian and such that B3 is equal to 0. And according to the previous main result, the fourth term of the right series is equal to 0. Okay, so recall that one way to describe finally generated groups can be done by means of finite presentations. And finite presentation, we know that the finite presentation is given by the quotient of a free group over a finite set with a quotient with a finite set of relations. So if we want to describe finally generated left nilpotent braces of class 2, we aim to find a free object in the category of R-generated left nilpotent braces of class almost 2. So we want to construct first a left nilpotent brace of class 2. It must be R-generated, and so that for every R-generated left nilpotent brace of class most 2, this can be seen as a quotient of our free object B. Okay, so we know that we have that a skew brace consists of two group operations, so we need to define both or we need to describe both the additive group and the multiplicative group of this free object. Okay, so the first result is so we can assume that for the first main result, we can assume that B is left nilpotent of class at most 2. And we can assume that B is R-generated. So it is generated by a set of elements B1 to BR. So in this case, the first thing that we can prove is that the additive group can be written in terms of a sum of 3 subgroups. Sorry, where the first subgroup is given by the set of all finite sums of all possible finite sums of elements of the generating set. The second subgroup is given by the set of all finite sums of all possible star products of an element of two elements of the generating set. And finally, the third subgroup is the set of all finite sums of all possible 3 star products of elements in the generating set, iterating the star product on the right. And we have to stop here because recall that if B is left nilpotent of class 2, the fourth term of the right nilpotency series is 0. So here we have the description of the additive group of such a brace. And as a consequence, we obtain also an upper bound for the rank of the additive group of B. We have that B, this upper bound, so this rank is less than R plus R squared plus R cubed. And this is because here we have one free index, here we have 2 free indices, and here we have 3 free indices. Okay, but in this case, we can go a step further. Our next result showed that if we pay attention to these 3 star products, we see the following series of equalities. If I is strictly less than j, then bi star bj and then star bk is equal to bj star bi and then star bk. So we have these 2 star products are equal if we commute I and j. As a consequence, in our previous result, we can improve our previous upper bound for the rank of an additive group because this set can be written in a more shortened way. Because this set of star products, of 3 star products of elements of the generating set, can be written as a disjunct union. Here, we are considering those star products where the first and the second index is equal and the third index is free. And here, according to this, we are considering all possible star products of 3 elements such that the first index is strictly less than the second one and the third index is free. So as a consequence, we obtain this improvement of the previous upper bound. Okay, so we have describes our additive group. So now we need to find in order to define our free object in the category of R-generated left nilpotent braces, we need also to define a product. Okay, so if we want to define this object, of course, according to the previous result, we can set as the additive group a free abelian group over an alphabet X. And this alphabet is described as a union of indices according to the previous description given. So this union of indices is given. First, consider one free index. The second subset is a set of two free indices. And then for the star products of three elements, we have distinguished two subsets, so we can distinguish um, an element with two indices equal and the third one free, and an element with the first index strictly less than the second one and the third free. So if we consider this free abelian group over this alphabet, then it is possible to define a product also in this free abelian. This product is described in terms of the components of the elements appearing in this alphabet, and therefore we obtain that this is an this skew brace is an R generated brace generated by the elements x1 to xr. In addition, it is left nilpotent of class 2, and if we take any R generated left nilpotent brace of class 2, this brace is a quotient of our constructed free object. And these results, so these results have been published. The second main result with the description of finally generated braces is published in a recent work in the transactions of the London Mathematical Society, and the first result is also available in a preprint of arXiv. So that's all what I wanted to say. Thank you very much for your attention.
Thank you very much, Vicent, for your well-motivated and very interesting talk. Are there any questions from the audience? So we have a question in the chat saying
Okay.
the skew brace was defined as A times B plus C is AB minus A plus AC. Can we define it on the right-hand side as well?
Yes, of course. This has been defined on the left, but of course you can have a similar definition on the right, but clearly the development of the theory is equivalent, both on the left and the right. This is just a convention to consider the left side. Indeed, in the paper of Rome considered braces originally on the right side.
Thank you. A second question, but I think that's more an organizational question, is whether this recording will be on the website.
Sorry?
I assume so.
Sorry, the recording what?
Yeah, this is an organizational question about whether the recording is on the website, but I will guess yes.
Yes.
I also have a question, because you have this theorem, so you found an upper bound, knowing that your skew brace is left nilpotent of class 2, and then you found an upper bound for the right nilpotency class in terms of the nilpotency class of the additive and the multiplicative group. Yeah, there on that slide. One further.
Okay. Yes. This upper bound is effective because we have exactly an example of left nilpotent brace of class 2, and it is right nilpotent of class 3.
Okay. Is it my question was actually, is it also effective outside? Because your example here is, well, if B plus is abelian, is it also effective outside of that
No,
class?
exactly. No, this we don't know yet if this
Okay.
is effective or not. We know that at least in our proof, we managed to prove that it is right nilpotent. This term of the right series is 0, but we don't have an example of showing that this upper bound is effective.
Okay, thank you. Are there any more questions from the audience? I don't see anything else in the chat. I don't see any hands. So if not, then we thank Vicent again for his amazing talk.
Yeah, thank you very much. Thank you very much. So I can stop it now. Okay.